Video demonstration PoC number 4 Man in the Middle, AI and Models for 5G Networks of the European MARE project. In this demonstration, the complete environment of PoC number 4 is presented, designed to validate the detection and mitigation of man-in-the-middle attacks via DNS spoofing in a fully Dockerized 5G network. On the left side of the diagram are the legitimate users, represented by smartphones and trains connected through G-Node B base stations. These users generate normal traffic and access the services deployed in the network. In the lower left corner, the attacker is also shown, equipped with a device connected to the network whose goal is to intercept DNS queries to redirect users to malicious services. At the top center is the control plane, where the main 5G core functions are deployed, including NRF, UDM, USF, UDR, PCF, AMF, SMF, and NCF. These functions manage user registration, authentication, slice selection, and network policy enforcement. In the lower center area lies the user plane, composed of the UPF and the UPF train, responsible for carrying user traffic to the network services and to the Internet. To the right of the user plane is the non-public network, NPN, where the services accessible to users are hosted. Among them are the legitimate DNS server, a legitimate web server, and a malicious web server controlled by the attacker. During the attack, the adversary impersonates the legitimate DNS to reply with the IP address of the malicious server, causing users to be transparently redirected to fraudulent content. In the upper right corner, the MARE security plane is shown, integrating the security functions developed in this PoC. The first is the Continuous Infrastructure Monitoring Security function, which captures metrics and DNS traffic. The second is the Early Predictive Attack Detection Security function, which applies artificial intelligence models to detect anomalies and predict the attack's evolution. The third is the Enforcement and Automated Mitigation Security function, responsible for automatically selecting and executing the necessary countermeasures to contain the threat. In addition to these centralized SFs, the involved nodes have monitoring tools that send data to the first SF for storage and cleansing. A mitigation SF is also shown being sent to the DNS node to stop the attack. Another node present is the orchestrator of the security plane, representing the integration with the SEPE, PASTE, and ASPO components. When an anomaly is detected, a security event is generated and sent to the MARE security plane, where the mitigation policy is validated and the corrective action is automatically deployed on the real infrastructure. Overall, this scenario demonstrates how the MARE project combines continuous monitoring, artificial intelligence, and automation to detect, predict, and mitigate DNS spoofing attacks in 5G networks and future 6G architectures. Before applying the mitigation actions, the security event generated by our PoC is sent to the MARE security plane, which is organized in several logical layers. At the top, in the interface layer, MARE exposes the entry points used to interact with the platform. This layer includes APIs and connectors for exchanging security events and telemetry, as well as Security Service Level Agreements, or SSLAs, which define the security objectives and policies that must be enforced in the network. Below this, the abstraction layer provides a normalized view of the infrastructure. It collects telemetry data, identifies the attack surface, and characterizes the monitored systems so that all components in the security plane have a common understanding of the network state and the assets being protected. The core decision-making logic is implemented in the Security and Privacy Engine, or SEPE. SEPE receives security alerts from the PCS and other monitoring tools, correlates them with contextual information, and determines whether a mitigation action should be triggered. Once a response is proposed, the request is forwarded to PASTE, the pre-assessment stress testing module. PASTE validates the selected action in simulation, emulation, or real testbed environments to ensure that the mitigation is effective and does not negatively impact the network before it is applied in production. Finally, the Adaptive Security and Privacy Orchestrator, or ASPO, orchestrates the deployment of the approved security functions. ASPO selects the appropriate playbook and coordinates the activation of the required mitigation components across the operational infrastructure. In summary, MARE provides an end-to-end framework where security events are received through the interface layer, contextualized in the abstraction layer, analyzed in SEPE, validated by PASTE, and finally enforced by ASPO. This architecture enables automated, safe, and adaptive security responses for 5G and future 6G networks. In this section, we present the main MARE security core components involved in this proof of concept. The SSLA module, SEPA, paste, system characterization, the three security functions developed in the PoC, and the ASPO orchestrator. Together, these components enable the end-to-end workflow from attack detection to automated mitigation. The continuous infrastructure monitoring function in the 5G core constantly gathers telemetry, then passes extracted features to the early predictive attack detection function. When this function identifies signs of a man-in-the-middle DNS spoofing attack, it creates an alert with evidence and predictions, which is sent to SEPA's recommender module to start MARE's decision-making and mitigation workflow. The detection event is described with the following information: event type, attack type, man-in-the-middle, source, destination, and attack details that explain what is happening at that moment. The attack details also include the identified consequences and supporting evidence of the attack. Finally, it is identified if the attack is predicted or detected. Once the attack alert reaches the recommender module, the intelligent decision-making phase of the MARE security plane begins. At this stage, the system analyzes the security event and starts evaluating how the detected threat can be mitigated in the most effective and safest way for the operational network. From all the information received in the alert, the recommender focuses on the most relevant parameters for the analysis, including the attack type, the source and destination involved, and the affected service. Using these parameters, the recommender queries the attack mitigation and preventive actions database to identify which security measures are valid and applicable for this specific attack scenario. At the same time, the recommender requests additional information from the system characterization module to obtain contextual awareness about the infrastructure. This includes understanding the role of each node, the active services, network dependencies, and the current operational state of the affected components. With this contextual information, the system can determine the most suitable locations in the network where the mitigation measures should be applied. Finally, combining the information, the recommender generates the final decision output. This output contains a prioritized list of mitigation actions together with the exact nodes and services where these security measures will be deployed. Once the recommender generates the mitigation decision, the output is forwarded to the playbook module, where the orchestration workflow preparation begins. The playbook communicates with the security function composer to translate the selected mitigation actions into deployable security functions that can be instantiated in the infrastructure. Using this information, the playbook generates a deployment workflow containing the selected security functions, the target nodes where they must be applied, and the contextual information related to the detected attack, such as the affected services and attack characteristics. Finally, the generated playbook is stored in the database to maintain traceability and control over security events, mitigation states, and orchestration processes across the MARE security plane. The generated playbook is sent to the paste module. Once the playbook reaches paste, the PAV component sends it to the Testing Environment Manager, or TM, which decides where the selected security functions should be validated. In this case, TM selects the emulated environment and sends the deployment information to the emulated testbed orchestrator. The orchestrator then deploys the selected security functions in the emulated infrastructure and continuously returns the execution status, updating the playbook with the validation and deployment results. During the validation phase, both the PAV and the SSLA modules participate in evaluating the deployed security functions. Once the security functions are deployed in the emulated environment, the impact on the network is analyzed again. The testbeds collect telemetry and monitoring data from the infrastructure and send the validation results back to the PAV component. At this point, PAV has information about both the original attack consequences and the network state after applying the mitigation actions. Using this updated context, PAV consults the SSLA module to verify whether the desired security objectives and operational conditions have been successfully achieved with the deployed security functions. Once the validation is successfully completed, PAV sends the approved deployment decision to ASPO. The ASPO orchestrator then takes the validated playbook and forwards the deployment information to the orchestrator of the real 5G infrastructure, which is responsible for deploying the selected security functions in the operational network and applying the mitigation actions against the detected attack.